ME204, Power and Efficiency. Power is defined as the rate of doing work. For example, it's the amount of work that's done per unit of time. We can write this in equation form as power, P, is equal to the work divided by a change in time. If power is equal to work divided by a change in time, and we know that work is equal to a force times a change in position or a distance, we can substitute this into our power equation and get that the power is equal to the force times a change in position divided by a change in time. Do you recognize this portion of the equation, change in position with respect to a change in time? This is just our velocity. So we can further reduce this so that our power is equal to a force times a velocity. When we considered work as force times a distance, we noted that the force and the displacement had to be in the same line of action. The same can be said for power. If power is a force times a velocity, the force and the velocity have to be acting in the same line of action. Work and power can be applied to other types of systems as well. If we consider what the pattern is, then we can figure out what the work and power is for other types of systems. Work is equal to a cause of the motion times the amount of motion that occurs. When we look at translation, the cause of motion is a force, and the amount of motion that occurs is a distance. So work is equal to a force times a change in distance. If we're to consider rotation, the cause of motion in rotation is a torque or a moment. The amount of motion that occurs is an angle. So work is equal to torque or a moment times a change in angle. For fluids, incompressible fluids, pressure causes the motion, and the amount of motion that occurs is measured as a volume. So work in a fluid system is pressure times a change in volume. For electrical systems, voltage causes the motion, and coulombs of charge is the amount of motion that occurs. So work is equal to the voltage times the coulombs of charge. For power, we look at the cause of motion times the rate of the motion that occurs. So for translation, the cause is a force, and the rate is a velocity. So power equals force times velocity. For rotation, again, the cause is a torque or a moment, and the rate of motion is an angular velocity. So power is equal to torque times an angular velocity. For incompressible fluids, the cause of motion, again, is a pressure, and the rate of motion is a flow rate. So our power is equal to pressure times a flow rate. And in electrical systems, voltage is the cause of the motion, and the rate of motion is a current. So power is equal to the voltage times the current. Let's consider the units of power. In a metric system, it's a Newton meter per second. Newtons is our force, meters per second is our velocity. But we can write this as a joule per second, knowing that a joule is a unit of work, or a Newton meter. A joule per second is also called a watt in the metric system. 1 watt is equal to 0.239 calories per second. In the English system, we have pound-feet per second. Pounds are the force, feet per second is the velocity. Typically, we see this written as a horsepower. There are 550 pound-feet per second for every horsepower. 1 horsepower is equal to 2,547 British thermal units per hour. If we want to relate the metric and English system, then 746 watts is equal to 1 horsepower. So where does the horsepower unit come from? The unit of horsepower was created by James Watt at the end of the 1800s. He compared the rate of doing work by a horse to a steam engine. During the test, he showed that a horse could lift 150 pounds of weight at an average velocity of 3.67 feet per second, and the horse could keep that up all day long without getting tired. So if we look at the force, 150 pounds, times the rate of work, 3.667 feet per second, then we get 550 pound-feet per second. This is 1 horsepower, and that's where it originates from. Let's look at a couple of examples. Example 1, how much power is required to keep an object flying in space at 500 meters per second? In this case, the object would be moving at a constant velocity. There's no forces acting on the object to cause it to accelerate or decelerate. It's simply moving at 500 meters per second. So our force is 0 when it's flying through space, if we're going at a constant velocity. If our force is 0, then 0 times our velocity is equal to 0. So no power is required to keep an object flying in space at 500 meters per second. Is any work being done? No. If there's no force, then we can't calculate work by multiplying force times the distance. Is the kinetic energy changing? There's no net force, so there's no acceleration, so my velocity can't change, and so my kinetic energy is not changing either. Let's look at another example. What if we have a 1,000-pound boulder, and we're trying to pull on that with 10 pounds of force? How much power is required to apply that 10 pounds of force? Well, the object isn't moving. I'm not going to move a 1,000-pound boulder with 10 pounds of force. So my velocity is 0. If my velocity is 0, then the force times the velocity is also equal to 0. So no power is required to put 10 pounds on a 1,000-pound block. What if the rock was moving at 8 feet per second? How much power would be required to keep it moving at that speed? Well, we want to know the force that's required to keep the rock moving at 8 feet per second. From the force, we could calculate what the power is. If we look at a free body diagram, knowing what our kinetic friction is, and knowing that the object is moving, then we would be able to figure out that the friction force is 0.3 times the normal force. If our normal force is 20 pounds, then our friction would be 6 pounds. There's no acceleration, we're going at a constant velocity, so this means that it's a static problem. The sum of the forces equals 0. If the sum of the forces equals 0, then looking at the forces in the x direction, the force that's being applied is 6 pounds. If the force being applied is 6 pounds and the velocity is 8 feet per second, we can calculate the power required to keep it moving at 8 feet per second by timesing 6 pounds by 8 feet per second to get 48 foot-pounds per second. If we want to convert this to horsepower, 1 horsepower is 550 foot-pounds per second. Our foot-pounds per second cancel, and we're left with 0.09 horsepower. If the rock is moving at 8 feet per second and we're applying a force at a 30-degree angle, how much power would be required to keep it moving at that speed? Again, we want to calculate the force that's required to keep it moving at 8 feet per second in order to calculate the power. There's no acceleration. This means it's a static problem, and the sum of the forces equals 0. If we draw our forces on the object, we can then sum the forces in the x direction, knowing that that will be equal to 0, and we would have our tension, T, times the cosine of 30, minus our friction, which is 0.3 times the normal force, equals 0. In the y direction, the sum of the forces also equals 0. So in this case, we have the tension times the sine of 30 plus the normal force minus the weight of 20 pounds equals 0. Solving these two equations simultaneously, we get the tension is 5.9 pounds and the normal force is 17 pounds. That means that our friction force would be 5.1 pounds. To calculate our power, remember that our power is the force times the velocity that act in the same line of action. So it wouldn't be the full 5.9 pounds that we would use as our force. It would be a component of that. Our power is equal to 5.9 times the cosine of 30 times 8, which is 40.9 foot-pounds per second. Remember, only the component of the force in the direction of the velocity contributes to the power. So we take the component of our 5.9 pounds that are acting in the x direction, which is 5.9 times the cosine of 30. Then we can calculate our power of 40.9 foot-pounds per second. Where is the power going to? If we're putting this power into it, and it's moving at 8 feet per second, where does that power go? Well, the power is used to overcome the friction of the system. So if we looked at it from the other direction, our power is equal to our friction times the velocity. So the power being taken out of the system is 5.1 pounds times our 8 feet per second, which is equal to 40.9 foot-pounds per second, which is the same as the power that's being put into the system. Why does it require less power to pull the rock at an angle? We got 40.9 in this case versus the 48 that we got in the other case when we were pulling straight on the object. Well, when we pull at an angle, we reduce the normal force, which in turn reduces the friction. So the power needed to overcome the friction is less when we pull at an angle. Can I get as much power out of an electric motor as I put into it? Here's an example of a motor. If I put electrical power into the motor, that spins the motor inside, and that is converted to mechanical power out of the system. If I put 1,000 watts into this motor, and I get 800 watts out as mechanical power, then my motor has an 80% efficiency. So I can calculate the efficiency of any motor or of any system as the efficiency being equal to the power out divided by the power in. Here's an example. We have a motor that pulls a 100-pound block up an incline at a constant velocity of 4 feet per second. We want to find the power supplied by the motor in horsepower and the power supplied to the motor in watts. So the power supplied by the motor is the output power of the motor. The power supplied to the motor is the input power. The coefficient of kinetic friction in this problem is 30%, and the motor has an efficiency of 75%. Well, let's start by drawing our forces on the object. Let's break our weight into components. This will help make solving this problem a little bit easier. We'll rotate our axes, and we can calculate the component of the weight in the y direction and the component of the weight in the x direction. Knowing the component of the weight in the y direction, we can figure out what the normal force is. And once we know the normal force and knowing that the block is moving, we can calculate the kinetic friction. So our friction is 26 pounds and our normal force is 86.7 pounds. Sum of the forces in the x direction equals 0. So we have our tension minus the 50-pound component of the weight minus the 26 pounds due to friction, all equal to 0, since we're going at a constant velocity. That means that our tension is 76 pounds. That's how much force the motor is pulling. If the motor is pulling 76 pounds and the velocity is 4 feet per second, then we can calculate the power as 76 pounds times 4 feet per second, which will give us 304 pound-feet per second. But we want to know this in horsepower. So we use our conversion factor of 1 horsepower equals 550 pound-feet per second. Our pound-feet per seconds cancel, and we're left with 0.55 horsepower. This is the power output of the motor. To calculate the input power, we use our efficiency equation, which is equal to the power out divided by the power in. Rewriting this equation for the power in, we get that the power in is equal to the power out divided by the efficiency. So 0.55 horsepower divided by 0.75. We want to see this in watts, so we use our conversion factor of 746 watts per horsepower, or horsepower cancel, and we're left with 547 watts. Our next topic will be kinetic energy of a rigid body.